Hello students, this is Shahista Godba and today I am going to teach you a short topic that is Gauss law. So it's state before telling you the statement, let me explain you what exactly we are going to study. So basically, suppose suppose you know how a current flows through any particular wire. So basically that is due to a charges that flows within it, right? Current is basically the rate of flow of charges per unit time. Now you know basically there are two types of charges. One is positive charge, and we may call it a positive charge, that is proton, and a negative charge that is electron. So suppose that here there is a positive point charge and here there is a negative point charge. Okay, so a point charge generates an electric field. So if this is a positive point charge, the electric field is going to generate somewhat like this, radially outward. So this is how your electric field is going to radiate. And for a negative test charge, a negative point charge, the electric field is going to radiate inward, somewhat like this way. So a point charge creates an electric field. Now suppose we are talking about a Gauss law. So Gauss law basically, let me write a mathematical formula for that. Phi is equal to closed integral of E dot ds is equal to q enclosed upon epsilon naught. Now let us understand this mathematical statement. First of all, you will notice here there is a symbol that is given as phi. So phi is basically a flux. Now what is flux? Flux is basically number of field lines passing or coming out through the surface. For example, if suppose this is a sphere and we took a small surface area of this sphere. For example, if you took a small surface area ds, or derivative of s, small surface, and this is that area, and if you place this particular positive charge inside this sphere, suppose this is the positive charge inside the sphere, so as you know the electric field is going to radiate outward, so that it is going to radiate outward through this sphere. So phi is basically what? Number of electric field lines coming out through the surface. So number of field lines that is going to come out through this particular small surface, that will nothing but your flux. More the number of electric field lines coming out through this surface, more will be the value of the flux. So that is basically your flux. But it is also given as flux is equal to closed integral of the dot or scalar product of two vectors. One is electric field and the another is ds. Now basically this is the closed integral, a closed surface. We are talking about a closed surface. Now basically the circle that we have assumed here is nothing but a Gaussian surface. For example, if we consider uh, if we consider this as a metal sphere, and suppose outside this is a Gaussian surface, outside this metal sphere is a Gaussian surface. Okay, so Gaussian surface is nothing but an imaginary circle, and if you want to measure, suppose at this point I want to measure electric field, so we consider this Gaussian surface a uniform surface, and we could able to measure electric field at this point due to this point charge q. So the Gaussian surface could be of any shape. It is not necessarily a circular or a spherical shape, but it must be a closed surface. There should not be any opening from the surface, Gaussian surface. But it depends upon the total flux depends upon the number of charge enclosed within the surface. So there will be the charges inside the surface and not outside this Gaussian surface. Why? Because if suppose we have took a charge over here, positive test charge, positive point charge. So the electric field is going to radiate outward somewhat like this. Suppose there are the two number of electric field lines entering the surface. If 2 is entering, then obviously 2 will be leaving out of the surface and nothing left inside it. But if you consider a point charge, a positive charge over here, you could able to see only the electric field lines radiating out from the surface like this way, radially outward. So the total electric field lines, suppose 1, 2, 3 coming out of the surface and nothing coming inside. So that's why we can say that the number of charges enclosed inside the surface that determines the flux, that is flux through that particular surface. So close integral of E dot ds. Now here there are two vectors given. One is electric field vector and the another is the surface area vector. Now basically ds vector is nothing but a normal to the surface. Normal in the sense, if this is the area that we are considering, so the ds vector will be normal to this particular area. And what about this electric field line? Electric field line is also radiating outward like this way. Suppose this is the whole sphere and here is your positive charge. So the electric field line, electric vector or electric field line is radially outward. You may notice that the area vector and the electric field are in the same direction. This is the ds and this is the electric field vector. They are both in the same direction. They are in parallel to each other. So when the two vectors are parallel to each other and we take a dot product, this is the dot product or scalar product. So when you take a dot product of two vectors, for example E dot ds, you write it as magnitude of E into magnitude of ds cos theta. Now you may observe that the angle between these two vectors is 0 degree. So cos 0 degree will be equal to 1. So we will get a magnitude E ds. If in case these two vectors are perpendicular to each other, if this is the area vector and this is the electric field vector, theta is equal to 90 degree. So the total flux will be cos 90 degree. If theta is equal to 90 degree, cos 90 degree will be 0 and hence the total flux will be 0 because flux is equal to close integral of E dot ds, that is equal to E ds cos 90 degree, and 90 degree is equal to 0 and hence flux is equal to 0. So a flux is going to be having some finite value when theta is equal to 0 degree, and the flux is going to be 0 when the two vectors are perpendicular to each other, that is theta is equal to 90 degree. So from here we see that when we take a close integral of two vectors such that these two vectors are parallel to each other, that equal to total charge enclosed upon epsilon naught. Now Q enclosed is basically, as I've told you, all the charges must be present inside the Gaussian surface. It should not be outside the Gaussian surface. All the charges outside the Gaussian surface will not be counted and will not lead to any flux. Hence, all the charges present inside the surface will only contribute to the total flux.